78 feet. That's how far below the surface of the East River 600 men worked every day, breathing air that was pumped into a wooden box the size of a city block, air compressed to 35 pounds per square inch, air that would slowly, invisibly kill them. They didn't know it yet. Nobody did. The doctors didn't have a name for what was happening inside their bodies. The engineers didn't understand the physics. All they knew was that men would climb down into the caisson healthy, work a shift in the mud and the dark and the heat, climb back out into the daylight, and then collapse. Some went blind, some went paralyzed, some just dropped dead on the spot, blood foaming from their noses. And the man who designed the whole thing, the chief engineer of the most ambitious bridge ever attempted in the Western Hemisphere, would become one of its victims. Washington Roebling went down into that caisson one too many times, and it nearly killed him. He spent the next 11 years directing construction from his bedroom window with a telescope, watching other men finish the bridge that was destroying him from the inside out. But here's what makes this story different from every other construction tragedy you've ever heard. When Roebling couldn't leave his bed, his wife Emily didn't just relay messages, she taught herself higher mathematics, materials science, cable construction, and structural engineering. She met with contractors, she briefed politicians, she fought off a board of trustees that tried to fire her husband. For 11 years, a woman in Victorian America ran the largest, most expensive, most dangerous engineering project on the continent. And almost nobody gave her credit for it. This is the story of the Brooklyn Bridge, not the postcard, not the skyline icon, the blood and the pressure and the debt that was paid in human bodies so that you could walk across it today. The East River in 1869 was not the East River you see now. Today it's hemmed in by seawalls and promenades and bike lanes. In the years after the Civil War, it was a churning, filthy, dangerous tidal strait that separated two of the most important cities in the Western Hemisphere. Brooklyn was its own city then, the third largest in America. Manhattan was already the commercial heart of the nation, and the only way across was by ferry. Those ferries ran from dawn until late at night, carrying hundreds of thousands of people a day. Businessmen, factory workers, dock workers, families. The crossings were miserable in summer, with the stench of raw sewage and rotting fish rising off the water. In winter, they were lethal. Ice floes jammed the strait, sometimes completely, sometimes for days at a time. In the brutal winter of 1867, the river froze so thoroughly that ferry service stopped entirely. Tens of thousands of workers were stranded on the wrong side of the water. Food supplies were cut off. Commerce ground to a halt. People died of exposure waiting on the docks. The economic damage ran into the millions. Everyone knew a bridge was needed. People had been talking about it for decades. In 1852, the engineer John Roebling himself had first proposed a suspension bridge across the East River, and the idea had been laughed off as fantasy. Suspension bridges were for valleys and gorges, not for busy maritime channels in the most commercially important waterway in the United States. But by the late 1860s, the laughter had stopped. The ferries were killing people with numbing regularity. Passengers fell between the boat and the dock. Overcrowded vessels listed and swamped. Collisions in fog sent men and women into water so polluted it was nearly toxic. And every hard winter, when the ice locked the strait, the economic consequences were devastating enough to make the impossible start looking necessary. The problem was the engineering. The East River is not a river at all, but a tidal strait connecting the Upper Bay to Long Island Sound, and the currents move fast. The crossing at the proposed site measured roughly 1,600 feet, nearly twice the span of the longest suspension bridge in existence at the time. And the Cincinnati-Covington Bridge that John Roebling himself had built, and you couldn't put a pier in the middle. The East River was a vital shipping lane. Any bridge had to clear it in a single span, high enough for the tallest masted ships to pass underneath. The man who said it could be done was John Augustus Roebling, a Prussian-born engineer who had immigrated to America in 1831 and built his reputation on wire rope and suspension bridges. Roebling was meticulous to the point of obsession. He calculated wind loads, temperature expansion, dynamic stress from moving traffic, the weight of snow accumulation. He designed towers that would rise nearly 300 feet above the water, cables that would carry thousands of tons, and a roadway that included separate lanes for pedestrians, horse-drawn carriages, and a rail line down the center. His design had a safety factor built into every element. He overbuilt everything because he understood that the forces acting on a suspension bridge were not fully predictable, and he refused to leave margin to chance. His plans were approved in 1867. The New York Bridge Company was incorporated. Political support came from William Boss Tweed, the corrupt head of Tammany Hall, who saw the bridge as a patronage gold mine and pushed the state legislature to authorize it. Tweed would eventually be brought down by his own corruption, but not before he had ensured the bridge's political survival in its earliest, most vulnerable phase. It's one of the strange ironies of American infrastructure that some of the greatest public works projects were built, in part because crooked politicians saw a way to profit from them. The bridge outlasted the graft. It always does. Construction was authorized. John Roebling would oversee the greatest engineering achievement in American history. He never laid a single stone. On June 28, 1869, John Roebling was standing on a rack of pilings at the Fulton Ferry slip in Brooklyn, surveying the site for the Brooklyn Tower. An incoming ferry pinned his foot against the pilings, crushing his toes. They were amputated. Tetanus set in within days. On July 22, 1869, less than a month after the accident, John Augustus Roebling was dead at the age of 63. The bridge that was supposed to be his masterpiece had killed its creator before a single foundation stone was placed. The project passed to his 32-year-old son, Washington Augustus Roebling. Washington was a Civil War veteran who had fought at Gettysburg, crossed the Rappahannock River under fire in a reconnaissance balloon, and earned a reputation for calm under conditions that would break most men. He had trained under his father for years. He understood the plans, the physics, the materials. But what Washington Roebling was about to face had nothing to do with battlefield courage. He was about to go underground. The fundamental challenge of the Brooklyn Bridge was not the span, it was the foundation. The two granite towers that would anchor the cables had to rest on solid bedrock beneath the riverbed. On the Brooklyn side, on bedrock lay roughly 44 feet below the water surface. On the Manhattan side, it was estimated at nearly 80 feet down. Between the water surface and the bedrock was a mess of silt, mud, gravel, glacial boulders, old ship timbers, and the accumulated waste of 2 centuries of waterfront civilization. You couldn't build on that. The towers would weigh tens of thousands of tons each. They needed bedrock, which meant someone had to dig down through the riverbed, clear away everything on top of it, and build a foundation at the bottom. The technology Roebling chose was the pneumatic caisson. And if the word caisson sounds clinical, let me describe what it actually was, because it was one of the most harrowing work environments ever created. Picture a wooden box, 168 feet long, so 102 feet wide, roughly half the size of a football field. The roof is a solid mass of yellow pine timbers, 15 feet thick, bolted together in alternating layers, and sealed with tin plating, oakum caulking, and hot pitch. The walls angle inward toward the bottom edge, creating a cutting shoe of iron that bites into the riverbed. The whole structure weighs approximately 6,000 tons empty. When it's in position on the river bottom, compressed air is pumped in through iron pipes, displacing the water and creating a pocket of breathable atmosphere underneath the massive wooden ceiling. Men enter through airlock shafts, iron tubes, 3.5 feet in diameter, that run vertically from the surface down through the caisson's roof and into the work chamber below. To get in, you step into a small pressurization chamber at the top of the shaft. The door seals behind you. Then the hissing starts. Compressed air fills the chamber. The pressure builds against your eardrums until the pain is sharp and constant, like a spike being driven into each side of your skull. Your sinuses feel like they're being crushed inward. Your teeth ache. Your vision blurs. The equalization takes several minutes. When the pressure inside the chamber matches the pressure in the caisson below, the bottom hatch opens and you climb down a ladder into darkness. The Brooklyn caisson was launched in March of 1870 and towed into position in the East River. as courses of limestone were laid on top of the caisson to form the base of the tower. The caisson's own growing weight drove it deeper into the riverbed. Inside, and men with shovels and pickaxes dug out the material beneath it, hauling mud, prying loose boulders, sawing through old ship timbers, and sending the debris up through water shafts to the surface. Every foot the caisson sank increased the air pressure needed to hold the river back. Every increase in pressure pushed more nitrogen into the blood of the men working inside. The conditions inside were almost beyond description. The temperature routinely exceeded 80 degrees Fahrenheit, even in winter, because compressed air generates heat. The atmosphere was thick, humid, and heavy, saturated with the smell of rotting wood, candle smoke, damp earth, and human sweat. Lighting came from calcium lamps that burned with an unnatural brightness in the pressurized air, and from candles that flared and guttered unpredictably. Sound traveled strangely. Men's voices were pitched higher by the dense atmosphere. The constant hiss of incoming air became a background drone that you stopped hearing. After the first hour, but that never actually stopped, the floor was river mud, not clean sediment. This was the bottom of the East River in the late 19th century. Sewage, industrial runoff, animal carcasses, rotting vegetation, and centuries of harbor waste, all compacted into a thick, stinking paste that clung to your boots and your tools and your skin. Men stood in it up to their ankles. They dug through it by hand. When they hit boulders too large to move, they broke them apart with pickaxes and chisels. When they encountered old timber pilings from long-demolished wharves, they sawed through them by hand in the pressurized dark. Like the work was medieval in its physicality. The technology surrounding it was cutting edge. The contrast was obscene. Shifts ran 4 hours initially. As the caisson sank deeper and the pressure increased, shifts were shortened to 3 hours, then 2. The men were paid roughly $2 a day, about $60 in today's money. For comparison, a skilled carpenter on the surface earned about $3 a day without risking his life underground. The caisson workers received a modest premium for the danger, but not enough to reflect the reality of what they were enduring. They were mostly Irish and German immigrants, men with families, men who needed work badly enough to climb down an iron shaft into the bottom of a river for wages that barely covered rent in a Lower East Side tenement. Many of them had survived famine, war, or the Atlantic crossing itself. They were not weak men. They were not ignorant men. They simply had no way to know what the air was doing to them, because nobody on Earth understood it yet. The foreman ran the shifts below with iron discipline. The caisson was divided into work sections, and each crew was assigned a quadrant. Communication was difficult. The dense air distorted sound, and the constant noise of shovels scraping stone, picks striking boulders, and the relentless hiss of compressed air made it hard to hear anything at all. Hand signals became as important as shouted orders. When a boulder was too large to break by hand, the men drilled holes, packed them with small charges of blasting powder, and detonated them in the confined space. The concussions in that pressurized environment were brutal. The shockwave hit your chest like a fist. Your ears rang for hours afterward, and the smoke and dust had nowhere to go. It hung in the air, thick and acrid, until the ventilation pipes slowly cleared it. The men who worked the caissons developed their own culture, the way any group of people does when they share a daily confrontation with death. They had nicknames for the worst sections. They had superstitions about which shaft to enter. They could tell by the sound of the air pumps whether the pressure was holding steady or dropping, and a drop in pressure meant water seeping in, which meant everyone moved faster and nobody spoke. They were tough and they were brave, and they were being slowly poisoned by the atmosphere they worked in. In December of 1870, the Brooklyn caisson nearly became a mass grave. A fire broke out in the timber roof, ignited by a candle flame that caught in the dried oakum caulking near the ceiling. In the pressurized atmosphere, fire behaved differently than on the surface. The compressed air was dense with oxygen. It fed the flames, making them hotter and more aggressive than any surface fire. Smoke filled the work chamber rapidly, thick and choking, with nowhere to vent. Washington Roebling was inside the caisson when the fire started. He stayed. He organized crews to pump water into the timbers. He directed the firefighting effort for hours while the smoke thickened and the temperature climbed. The battle went on through the night. Roebling spent nearly 7 consecutive hours in the pressurized caisson, far longer than any safe exposure window. When the fire refused to die despite hours of water, Roebling made the agonizing call to flood the entire caisson, killing the fire by drowning the work chamber completely. It took days to pump the water back out and assess the damage. The timber ceiling was charred in places, weakened, but intact. Construction resumed. The fire set the schedule back by weeks, and it put Washington Roebling's body on the clock that would eventually destroy it. The Brooklyn caisson reached its target depth in the spring of 1871. At 44 feet below the surface, Roebling made a critical decision. Bedrock was close, perhaps just a few more feet down, but reaching it would require blasting through a layer of compacted gravel and stone. The explosions might compromise the caisson's integrity, which might crack the timber ceiling that was the only thing between 600 men and the full weight of the East River. He ran the numbers. He tested the soil. He calculated the bearing capacity of the compacted sand and gravel beneath the caisson's floor. And he made the call. Seal it here, fill it with concrete, build the tower on top of it, and trust the math. That gamble has held for over 140 years. The Manhattan caisson was worse. Everything about it was worse. It was launched in 1871 and positioned on the New York side of the river, where the Geological Survey indicated bedrock at a far greater depth. The caisson had to sink to 78 feet below the water's surface. At that depth, the air pressure inside the work chamber reached 35 pounds per square inch, more than double normal atmospheric pressure. The heat was suffocating. The work was slower because the material at that depth was harder, denser, packed down by the weight of everything above it, and the toll on the human body was catastrophic. Caisson disease, the bends. The workers had been experiencing symptoms since the Brooklyn caisson, but the Manhattan side turned it into an epidemic. The science wouldn't be properly understood for decades, but here is what was happening inside those men. At 35 pounds per square inch, the compressed air forced nitrogen gas to dissolve into the blood, the tissues, the fluid in the joints, the fat around the spinal cord. As long as the men stayed under pressure, the nitrogen remained dissolved and harmless. But when they decompressed in the airlock, when they ascended back to normal atmospheric pressure, the nitrogen came out of solution. It formed bubbles, tiny, invisible, agonizing bubbles in their knees, their elbows, their shoulders, their spinal cords, their brains. The symptoms were horrific in their range and unpredictability. Joint pain so severe that grown men couldn't straighten their limbs, doubled over and screaming, hence the name the bends. Temporary blindness that struck without warning. Paralysis of the legs that lasted hours, days, or forever. Seizures, ringing in the ears, nosebleeds that wouldn't stop, confusion, memory loss. And for some, with no warning at all, sudden death. Men would finish their shift, walk through the airlock, step into the daylight, stroll a few blocks toward their homes, and collapse on the sidewalk. Dead. The coroner would write heart failure or apoplexy on the death certificate. But nobody connected it to the compressed air because the connection was invisible, delayed, and scientifically unexplained. Dr. Andrew Smith, the bridge company's physician, documented over 100 cases during the Brooklyn caisson and many more on the Manhattan side. He was working blind, essentially. He tried hot baths, cold baths, electrical stimulation. He applied heated blankets to affected joints. He recommended shorter shifts and slower decompression. Some of his recommendations were adopted. Many were overruled by the construction schedule. The caisson needed to keep sinking. The bridge needed to be built. The budget was already strained, and the men kept climbing down. Washington Roebling kept going down with them. He didn't have to. He was the chief engineer. He could have supervised from the surface, from a desk, from anywhere that wasn't 78 feet below a river. But Roebling believed in being present. He inspected the work himself. He tested the soil himself. He breathed the same poisoned air as his workers. And in the spring of 1872, the air finally broke him. He came up from the Manhattan caisson one evening and collapsed. The pain was total, a full-body assault that left him unable to stand, unable to see clearly, unable to think through the fog of agony. He rested. He tried to go back. He collapsed again. Each episode was worse. Within weeks, it was clear that Washington Roebling would never recover fully. He was partially paralyzed. His eyesight was damaged. He suffered from chronic nerve pain, crippling anxiety, and what we would today recognize as severe neurological injury. He was 35 years old, and his body was finished. But his mind was not, and neither was his wife. Washington Roebling moved to a house at 110 Columbia Heights in Brooklyn, a brownstone with a direct sightline across the river to the Manhattan Tower. He set up a telescope at his bedroom window, and for the next 11 years, from 1872 to 1883, he directed every element of the Brooklyn Bridge's construction from that room. Every cable calculation, every stone specification, every argument with contractors and politicians and penny-pinching trustees. All of it filtered through one person. Emily Warren Roebling became the bridge. She had married Washington in January of 1865, a month before the war ended. She was the daughter of Sylvanus Warren, a New York State assemblyman, and she had been educated at a level unusual for women of her era. She was sharp, composed, and by every surviving account, possessed a social and intellectual confidence that most men of her time would have found threatening. When her husband was incapacitated, she did not retreat. She advanced. Emily taught herself. She studied the mathematics of catenary curves, the load-bearing properties of steel versus iron, the chemistry of Portland cement, the specifications for wire cable testing. She didn't learn it casually. She learned it deeply enough to hold her own in technical conversations with the bridge's assistant engineers, men who had spent their careers in the field. She met with them daily. She relayed Washington's instructions, but she also interpreted them, adapted them to conditions on the ground, and made real-time decisions that couldn't wait for a round trip to Columbia Heights. She dealt with the contractors. She dealt with the steel and wire suppliers. She dealt with the inspectors and the city officials and the relentless, grinding politics of Tammany Hall, which viewed every public works project as an opportunity for graft. She managed egos, budgets, and timelines with the precision of a general and the diplomacy of an ambassador. And she did all of this in a society that did not believe women were capable of understanding engineering, let alone managing the largest construction project in the Western Hemisphere. In 1882, the Board of Trustees moved to replace Washington Roebling as chief engineer. The motion was championed by Abram Stevens Hewitt, a trustee and future mayor of New York, who argued that a bedridden man could not competently run a $15 million public project. Emily appeared before the board, and she presented technical reports on the bridge's progress. She answered detailed engineering questions. She demonstrated such total command of the project's status, materials, schedule, and structural calculations that the motion to fire her husband was defeated. She had outperformed every man in that room, and the bridge survived because of it. Above the sealed caissons, the towers rose, 276 feet of granite and limestone, each tower containing roughly 67,000 cubic yards of masonry. The stone was quarried in Isaac G. Perry's quarries near Hallowell, Maine, and from quarries in upstate New York. Each block was cut by hand, numbered, shipped by barge down the coast and up the river, and hoisted into position by steam-powered derricks that swung loads over the heads of the workers below. A single drop stone, a single broken cable, a single failure of the hoisting mechanism, and men died. The margin for error was zero. The masons who laid those stones worked at heights that would shut down a modern construction site. There were no harnesses, no safety nets, no guardrails of any kind, just leather-soled boots on wet granite ledges, 270 feet above a tidal strait, with a current strong enough to drag a grown man under in seconds. The wind at that height was constant. In winter, ice formed on the stone surfaces and the iron frameworks. When a man lost his footing, he fell, and nobody survived a fall from that height. The body hit the water or the scaffolding below, and the crew paused briefly. and then work resumed because the schedule didn't stop for funerals and the stone didn't lay itself. Yet at the base of each tower, on both the Brooklyn and Manhattan sides, enormous anchorages were built to hold the cables. These were not delicate structures. Each anchorage was a solid mass of granite and limestone, roughly the size of a city block, weighing approximately 60,000 tons. The cables would loop around massive iron anchor plates buried deep inside these stone mountains. The anchorages had to be heavy enough and strong enough to resist the pulling force of the cables, which at full load amounted to thousands of tons. They were, in their own quiet way, as impressive as the towers. You can still see them today, squat and massive and almost forgotten next to the drama of the bridge itself. With the towers complete and the anchorages in place, the cables were strung. This was John Roebling's signature innovation. A wire cable spun in place across the span. A traveling wheel carried individual galvanized steel wires back and forth between the massive stone anchorages on each shore. The process was painstaking. Each wire had to be laid at precisely the right tension, the right sag, the right position within the strand. Too loose, and the cable would be weak. Too tight, and it would snap under temperature changes or dynamic loads. The wire spinners worked on catwalks strung between the towers, narrow wooden platforms suspended hundreds of feet above the river. The catwalks were less than 4 feet wide. There were rope handrails, but they offered psychological comfort more than actual safety. The wind at that height was ferocious, especially in winter, and the catwalks swayed. Men walked across them carrying tools, adjusting wires, inspecting splices. One misstep, one gust, one moment of lost balance, and you were falling 270 feet to the river. Several men fell during the cable spinning phase. Their bodies were recovered from the East River or pulled off the stone anchorages below. The wires were bundled into strands, 19 strands per cable, and the strands were compacted under hydraulic pressure and wrapped tightly with more wire to form a solid cylinder. Each of the 4 main cables is 15 3/4 inches in diameter and contains 5,434 individual wires. Unspooled, the wire in a single cable would stretch over 14,000 miles. That's more than halfway around the Earth, woven strand by men standing on a plank above the East River. The wire came from J. Lloyd Hayes Company, and this is where the story's ugliest chapter unfolds. Hay was supplying wire that failed the bridge company's quality tests. Rather than fix his process, he bribed an inspector named Elijah Heisted to swap approved wire for the rejected batches. By the time the fraud was discovered, an estimated 221 tons of substandard wire had been woven into the cables. It couldn't be removed without dismantling the cables entirely. Washington Roebling, communicating through Emily, recalculated the cable strength and determined that even with the defective wire, the cables retained a safety factor of at least 6-1. The bridge would hold, but the betrayal stung. Men had given their bodies and their lives to build this bridge with integrity, and a wire merchant had poisoned it for profit. Hay was eventually imprisoned for unrelated financial fraud. The defective wire remains in the cables today, 142 years later. The roadway was suspended from the cables on vertical suspender wires and reinforced by diagonal stay cables running from the towers to the deck. Washington Roebling had insisted on both systems, understanding that the combination would create a structure far more rigid than a conventional suspension bridge. His instinct was sound. Bridges built with only one system have failed. The Brooklyn Bridge has not. 14 years. From the day John Roebling crushed his foot in June of 1869 to the day the bridge opened on May 24, 1883. 14 years, $15.5 million in construction costs alone, roughly $320 million in today's dollars, and at least 27 confirmed worker deaths, each with the real number almost certainly higher. Dozens more were permanently disabled by the bends. One founding engineer killed before construction started. One chief engineer crippled for life. One woman who held the entire project together for over a decade while history tried to forget her. Opening day was unlike anything New York had ever seen. The bridge was decorated with flags and bunting. President Chester Arthur traveled from Washington to walk across it with Governor Grover Cleveland and Brooklyn Mayor Seth Low. Artillery batteries fired salutes from both shores. Ships in the harbor blew their horns. Bands played on the promenade. Emily Warren Roebling rode across in the first carriage, carrying a rooster as a symbol of victory, a tradition from her era that signified conquest and triumph. It was a small, strange, a beautiful gesture, and it was her right. She had earned it more than any other living person. Washington watched from his window on Columbia Heights. He could see the crowds. He could see the flags. He could hear the cannons faintly across the water. He could not be there. The bridge he had given his health to build was celebrating without him. Whether that was painful or peaceful, only he knew. An estimated 150,000 people crossed the bridge in the first 24 hours. They paid a penny each for the privilege of walking the pedestrian promenade, elevated above the roadway, with the cables rising on either side and the river spread out below them. The views were stunning. The structure was magnificent. People wept openly. Newspapers called it the eighth wonder of the world. And it was the longest suspension bridge on the planet. It was beautiful, and it was about to kill again. 6 days later, 12 people were dead. On May 30th, 1883, Memorial Day, the bridge was packed with pedestrians. A woman stumbled on the narrow stairs near the Manhattan Tower. Someone behind her screamed. The scream triggered a chain reaction in the dense crowd. Someone shouted that the bridge was collapsing. It was not. The structure was immovable. But the crowd didn't know that. Panic spread faster than any fact could travel. People crushed forward. They crushed backward. They crushed each other against the iron railings, against the stone walls, against the narrow stairway that became a choke point and then a death trap. 12 people were trampled to death. Dozens more were hospitalized with broken bones and crush injuries. The bridge that had taken 27 lives to build took 12 more before its first week was finished. You can walk across the Brooklyn Bridge today. It takes about 30 minutes if you keep moving. Most people don't. They stop for photographs. They admire the Gothic arches, the web of cables, the skyline frame between the towers. They lean on the railing and look down at the water moving beneath them. On a summer evening, the promenade is packed with tourists, joggers, couples, street performers. It feels festive. It feels safe. It feels like it has always been there. It has not always been there. It was built by hand, stone by stone, wire by wire, shovelful by shovelful, by men who were paid $2 a day and who did not know if the air they were breathing would let them walk home at the end of their shift. They don't think about what's underneath. Below the roadway, below the granite towers, below the riverbed itself, the caissons are still there. 2 wooden boxes the size of city blocks, sealed with concrete and pitch, sitting in the dark where 600 men once shoveled river mud by candlelight. The yellow pine has survived because it has been submerged and sealed from oxygen for over a century and a half. The caissons are the foundation. They will be there as long as the bridge stands. They are the bridge's secret, its buried cost, its hidden architecture. Washington Roebling lived until 1926. He was 89 years old. He never fully recovered from the bends. The pain, the damaged vision, the anxiety, all of it followed him through 5 decades. He outlived the 19th century and most of the men who built his bridge. He saw automobiles cross it. He saw it become a symbol, a postcard, a thing people took for granted. He knew what it cost. He carried that knowledge in his spine and his blood and his failing eyes for the rest of his life. Emily Warren Roebling earned a law degree from New York University in 1899 at the age of 56. She traveled widely. She wrote and lectured. She advocated for women's access to education. She died in 1903, 20 years after the bridge opened. A bronze plaque was eventually affixed to the bridge in her honor, acknowledging her contribution. It came decades late, and it says less than it should, but it's there. The workers, the caisson men. Most of their names are gone. Payroll records survive in fragments. First initials and surnames scratched into ledger books that have been sitting in municipal archives for a century and a half. Medical reports are incomplete and often vague, listing symptoms like pain in the limbs or nervous debility without connecting them to compressed air. They were immigrants, mostly Irish and German, some Italian, men who had come to America seeking something better and found themselves 78 feet beneath a river, breathing air that was dissolving their bodies from the inside out. Some of the survivors of caisson disease spent the rest of their lives in chronic pain. They walked with canes at 35. They couldn't work manual labor anymore. Some became beggars. Some were supported by their families. Some simply disappeared from the records. Men who built a national landmark and then vanished into the anonymous poverty of 19th century New York. They weren't compensated for their injuries. There was no workers' compensation in 1870, no disability insurance, no legal recourse, and no union strong enough to demand justice. If the job broke your body, you went home and you suffered, and nobody owed you a thing. 27 confirmed dead, dozens more permanently broken, one chief engineer crippled, one founding genius killed by a ferry, one woman erased from the story she made possible. There's a temptation, when you tell a story like this, to tie it up in triumph, to call it a monument to American engineering, to grit, to the unstoppable spirit of progress, and leave it shining in golden light. And it is those things. The Brooklyn Bridge is a masterpiece. The engineering holds up. The design is beautiful. The cables are sound. It carries over 100,000 vehicles a day now, loads that John Roebling never imagined, and it bears them without complaint. Today, we have OSHA regulations, safety harnesses, fall protection systems, decompression chambers, atmospheric monitoring, workers' compensation, and entire departments of government devoted to making sure that what happened in the Brooklyn Bridge caissons can never happen again. We have these things because of what happened in those caissons. The bends, the deaths, the paralysis, all of it contributed to the body of knowledge that eventually made compressed air work survivable. The men who suffered were, in a medical sense, the unwilling test subjects for decompression science. Their pain bought our understanding. But it is also a ledger, and the entries on one side are measured in stone and wire and mathematics, and the entries on the other side are measured in compressed nitrogen and shattered spines and names that nobody wrote down. The next time you see a photograph of the Brooklyn Bridge at sunset, remember what holds it up. Not just the cables, not just the granite arches, the wooden boxes in the dark, the iron airlock shafts, the candlelight, the hissing of pressurized air into a sealed chamber, the men with shovels standing in river mud 78 feet below the surface, breathing air that was killing them one bubble at a time. That is the price of the bridge, and that price was paid in full. If stories like this matter to you, the kind that remember the workers and not just the monuments, subscribe and stay with us. We dig into the forgotten labor behind the structures and machines that built this country. And if your family has any connection to the Brooklyn Bridge, to the caisson workers, to the masons, to the wire spinners, or to the trades that built New York in the 19th century, leave it in the comments. Those stories deserve to survive. The bridge will stand for another century, but the men who built it only last as long as someone speaks their names.